save on your PC. Yeah.
Okay. So as I was saying, like anyone from the audience would like to express their views on what they know about COMSOL. Anyone, like any random guesses, you would have heard about COMSOL a lot from your seniors and everyone.
Hello, am I audible?
Yeah.
So most probably what I think COMSOL is used for finding the fluid profile or the temperature profiles, or things like this, maybe in heat exchanger or a distillation column. I'm not sure, I guess.
Yeah, you are partially correct. Like that is one of the applications of COMSOL. So basically, so what COMSOL is, so COMSOL multiphysics is a platform where you perform finite element analysis. So I'm not sure like if all of you are aware of this term. So basically what finite element analysis means is, suppose you have some kind of a geometrical object. So what COMSOL does is it divides your entire domain, which is your object, into small elements. And then it solves the physics on those small elements. And then it integrates all of them and gives you the solution. So that is actually what is meant by finite element analysis and solver and a multiphysics simulation software. So by multiphysics, I mean that the best thing about COMSOL is that you can integrate various physics. Like as someone just mentioned, like suppose if you have a distillation column, so you have various processes going on. You have mass transfer, you have heat transfer, you have fluid mechanics, all of those things are going on. So all those multi-physics you can easily incorporate in COMSOL. And it's obviously a simulation software. Then the next thing is, it has a very user-friendly interface. So like instead of just like coding, like you don't have to write anything. It's just you have to click certain buttons and you have to enter certain parameters and then you are just done. So the interface is quite user-friendly and anyone, irrespective of which background they are from, they can easily use it. And next is, it has a coupled system of partial differential equation. So what this means is that if suppose you have a heat transfer equation or you have a fluid mechanics equation, so that involves certain ODs, some certain PDs, because sometimes you have to differentiate with respect to time, also with respect to your spatial variables like X, Y, Z. So all those partial differential equations are being solved in COMSOL using this finite element analysis, which I just mentioned. Okay, so that is basically what all is going on in behind the scenes of COMSOL. But we as like when you are doing through its user interface, you are not actually getting that feel, but this is the background. And then it provides a unified workflow. So in a minute, I'll be making you understand what does this workflow means. So it provides a workflow for, like you can see there are various physics involved. It is electrical, mechanical, fluid, acoustics, and various chemical applications. So it's not just heat transfer or fluid mechanics. There are various other physics that you can also simulate on COMSOL. It can be electrical, it can be mechanical, etc. Okay, so now this is a glimpse of some of the physics modules which are present in COMSOL. So as you can see, like the first one is AC/DC, acoustics, chemical species transport, electrochemistry, fluid flow, heat transfer, optics, plasma. So you can see all these physics you can simulate in COMSOL. And now if we go much deeper, then in each physics module, there are some specific physics that you can apply in your simulation. Like suppose if you drop down this electrochemistry, you find the first one, which is primary and secondary current distribution. Now, if you go down much further, you find more physics. So this is how all the physics are being integrated into COMSOL. Okay, so COMSOL workflow. So the best thing about COMSOL is that this workflow is common for all the physics. Like this is not just for any fluid flow or heat transfer problem that I will illustrate today, but it's valid for any kind of problem that you want to simulate in COMSOL. So the first step is always to set up your model environment. The second one is building the geometric objects. Third one is to create definitions. Fourth is to specify material properties. Fifth, you have to define certain boundary conditions, and then you have to mesh it. This meshing is actually that finite element analysis that I was talking about. Then you have to run your study and you can post-process. So all these processes, like they will become more clear to you as we'll go through an example. So, okay, so now we come to the first example that I'm going to illustrate today, which is Joule's law of heating. So like this, we all have learned it in our school times. So basically, Joule's heating, what it means is that suppose you have a conductor and you pass an electric current through it. So you know that every conductor it has a finite thermal conductivity. So they're not perfect conductors. So they have some kind of resistance in it. So when you are passing an electric current through it, what you will expect is that conductor will get heated. Okay. So this is what today we are going to simulate in COMSOL. So let me, is my COMSOL interface visible?
Yeah, it's visible.
Okay. Okay, so this is the first screen that you will encounter when you open COMSOL. So what we have to do, we have to first create a new model. So you go to File and then you click New. So here you encounter the two options, Model Wizard and Blank Model. So if you click blank model, you just go to that first screen that I just showed. But as I mentioned, the first step of the workflow is to set up your model environment. So that is done by clicking on this Model Wizard. So basically, we will specify certain specifications that we want in our model, and COMSOL will do that for us. So if I click on Model Wizard, so this is the dimensions, like in which dimension is your model being created. So as I just showed you now in this problem, okay. So in this problem, you can see that today we are going to simulate a bus bar, and these are 3 bolts. So does anyone have any idea like where do we use these bus bar, or if anyone have heard of this object before? Any random guesses?
Electrical circuit.
Maybe for connecting two parts.
Yeah, so it's basically used in your switches and your electrical circuits. So it is basically used for connecting a high voltage device to a low voltage device. And since it's a conductor, so that helps. Okay, so this is what we are gonna simulate today. So you can see that our model that we are going to simulate is 3-dimensional. So this is what we are going to choose in our COMSOL as well. Just like keep in mind this diagram, okay? So first I'll explain what all dimensions we have. We have 3-dimensional as I just shown. Then we have 2D axisymmetric. So what does this mean is that suppose you have a cylinder, okay? So if we just look it from one side, the cylinder, it will look like a rectangle, and there's an axis which is going in from in between. So you can imagine that you have a rectangle and there's an axis going in between. So what you do is that you just simulate the half part of that rectangle. And then if you click on 2D axisymmetric, it will automatically apply all the physics that you have done on the half part to the other half part. So what axisymmetric is actually an object which is symmetrical about certain axes. Okay. So that is axisymmetric. Then you have simple 2-dimensional, like if suppose you don't have any symmetry, then you have 1D axisymmetric. So that logic extends here as well. And then you have 1-dimensional. So 1-dimensional would be like just a line segment, and you are simulating on that. So basically on that line segment, you are creating certain segments, and the COMSOL is applying that physics on those segments and giving you the results. And then you also have a 0D, which is points. Okay, so for our example, we are interested in 3D. So I've clicked on that. Now, based on what you have chosen in your dimensions, the COMSOL, it gives you the physics accordingly. Like, it is all dependent on what all choices you make at every step. So I chose 3D. Now I have various physics modules that I showed you in the slides. So for this problem, we are interested in Joule heating. So that is present. First, you have to click on the heat transfer. Then you have to click on electromagnetic heating. And then you have to click Joule heating. So you can see the entire description, like what all will happen. So the Joule heating, it is used to model resistive heating. And this line is quite important. This multiphysics interface adds an electric current interface and a heat transfer in solids interface. So suppose I click on add, like to add any physics, you have to click on this button. Now, yeah, so you see that COMSOL has added the Joule heating interface, and it has automatically added the electric current and heat transfer in solids. So you see that COMSOL is quite smart in that sense, that because it knows that if you're simulating a Joule heating problem, then there will be an electric current and there will be a heat transfer in solid. It will be definitely involved. Okay, and that is the best thing about COMSOL. Okay, and so now you see that we have two different physics involved, currents and heat transfer. So this multi-physics is actually what it is doing it is coupling both these physics. Okay, so what it does is, what all information you enter in electric current, it is getting transferred into the heat transfer in solids interface. So it's acting as a bridge between the two interfaces. So that is why we call it a multi-physics. So this multi-physics, which is named as electromagnetic heating, is responsible to couple electric currents and heat transfer in solids. Okay, so also if you guys have any doubt at any point, just like don't hesitate to interrupt. So yeah,
Can I ask?
Yeah, definitely.
Sorry, actually I have a question. If I made a 3D geometry, can I transport to any CFD model like OpenFOAM or ANSYS plate, the geometry from here?
Yeah, you can export the geometry. Like I'll go to that user interface and we'll be creating the geometry, so you can export it.
Okay.
Oh, yeah. So as we have chosen the electromagnetic so this electromagnetic physics, multi-physics has been added to our model. Now the next step, and also just make sure like there are certain dependent variables which are associated with each physics. So for the electric currents, we have electric potential, and for heat transfer in solids, we have temperature. Okay. Then after we have done this, we go to study. So
like, can we add other physics also in the same model other than electric and heat transfer, or
Yeah,
will it be fixed?
so basically, what all physics you think is like important or relevant to your model, you can add all of them. Like I can add one of heat and one of fluids, or I can add just fluids. So that combination can exist.
Oh, okay.
Yeah. So you see now, this electric current is of some other module. It's of AC/DC, and this heat transfer in solids is of heat transfer module. And this multi-physics is basically coupling both of them. So that is how it goes on. Okay. So then we go to study. So in study, basically study means like there are various studies like stationary, time dependent, and or like these I have not used much, but these are what you have also been like taught before. So stationary study means you will have heard in your CHE 251 course, steady state. So that is what is stationary study. So basically, if I click on this, you will see stationary study is used when all your variables do not change over time. Okay. So what this actually means is, suppose you have a container and it contains water. Okay, now you add ink. So when you add that ink, so just anyone like tell me, is it stationary at that time when you have just dropped an ink into that container?
No.
No, because at that time when you are adding it, the mixing is like happening and your concentration of that ink in the water is changing over time. Now suppose you keep it rested for like maybe 5-10 minutes. Okay, so after some time, what will you observe? You'll see that that ink seems to get mixed well, and you don't see much change in the concentration. So that is actually that stationary study that we are talking about, that we have allowed our model, our simulation, at like we have rested it and we are simulating it at that time when all the variables are not changing much with time. So basically the time that we are observing is very less as compared to the time in which the variables are changing. So suppose my concentration of that ink in the water, it will vary next in about 5 hours, but I am seeing it in the next minute. So I will see that it is not changing with time. So that is actually is the stationary study. Okay. And then the time dependent study is, as I just told, like when you have just dropped the ink, that is the time dependent study, that you have all the variables are changing with time. Okay. And these are some other studies as well, like some related to frequency and some other like I haven't used that much, but yeah, like if suppose you have any doubts, you can look out for that description. Okay, but these two are the most common. So for this example, we are going to do stationary study. So I click on this, and so the added study is now stationary, and now we are done setting up a model environment. Yeah, so you can see like what all you chose in that, or in all those steps, they have all been added in the COMSOL. So now I'm gonna like introduce you like what all is this. So this and this are quite identical. So this is just a toolbar where you can just like click on definitions and you get all of this. Now you can get all these functions also in this model builder. So this model builder is just like a model tree. Okay, and these are various branches of it, like global definitions, component definitions, geometry, materials, and this is the physics that you had chosen. Then you have mesh, then you have study. So you see that the order in which these bars are present, in the same order the model builder is present. And this is actually the workflow, that first you have to define, then you have to build the geometry, then you have to assign the materials. This is the workflow that you have to follow. So now, so first of all, we had set up our model environment. Now we are going to build our geometrical objects. So if you just look at this bus bar, so like in the interest of time, I'm not going to like build the entire object, but I'm going to import it. So, but I'll show you like how it is built. Okay, so to import any kind of geometry, what you have to do is click on file, then go to the application libraries. So here you click on COMSOL multiphysics, then you go to multiphysics. So here I have my busbar geometry that I have just shown you. So now you are going to open it and click no. So basically this entire geometry will be imported in your model directly. So you can see this entire geometry is there, and you can just like rotate it and you can visualize it completely. And so see like what all operations have gone into creating this geometry. So first you have a work plane, you have a plane geometry, then you view it, then you extrude it. So just in the interest of time, I didn't build all of it, but in the further examples, which are much simpler, I'll make it for you. So in this example only I've imported. So you can see what, yeah.
Hello, ma'am. Can you please create a 3D geometry of any simple product like a cylinder or anything, if time permits?
Yeah, like in the next example, it will be a pipe, so I will make that.
Okay.
Yeah. Okay, so I've built this bus bar. Okay, so this is I've imported. Now our geometry is completely like defined. We have built all the geometrical objects. Now you see in the global definitions, there's a thing called parameters. So what this parameters means is that you are basically making your entire simulation parametric in terms of parameters. So suppose you want to change your parameter at any point of time, just change it here and your parameters will be updated. Okay. So this is all the parameters that we will use in the entire simulation. So if suppose you want to, at some point of time, you want to use this bolt radius. So you just have to mention rat _1, which is case sensitive. So it will automatically use this value 0.006. So in the further steps, I'll show you how to do that as well. Okay, so we have built the geometry. Now the next step is to define. So you all will be like wondering, like the definition steps is before, but I have done geometry before. So basically this is done because in definitions, like you can see all these things are now open, but these things get opened only and when the geometry is specified. Okay, so whenever you are simulating in COMSOL, always define your geometry first and then you define certain definitions. Okay, so now I'm going to specify a definition. So go to selections and then choose explicit. Now what definitions exactly mean is that suppose you in this geometry, you see I have bolt, these are my bolts and this is my bus bar. So it can be a more complex geometry as well. But what I'm doing is I'm selecting a certain part of this geometry, which I will use for reference later. So that is what exactly in definitions you do. You define certain things. Okay. So in this, I'm gonna define my bolts. So you see, I have in bolts, I have 6 surfaces like this bolt and the behind and the front. So I have selected my first bolt. So you can see number 6 and 7. These represents the boundaries. So this is number 6, this is number 7. Similarly, I'm going to select my other bolts. So this and this. So simply just to select, you have to hover over it, hover the mouse, and it will become colored. So it will show that you have selected. So you see I have selected 6 surfaces and I'm going to name them bolts. The use will, like you will understand it in a bit, like after certain steps, you will understand its importance. But for now, it is that for a complex geometry, you define certain things so that it becomes easier to work with them further. Okay, so now we have defined our definitions. Now the next step that comes is materials. Okay, so now we are going to assign materials. So our bus bar is made of copper and our bolts are made of titanium. So to add any material, you click on materials and then you add material. Click on this. So you see there's a complete material library present in COMSOL. So there are some material libraries, some are built in, some are specific to certain physics. So we are going to use some built-in ones. First is the copper. So this is copper and you have to click on add to component. Okay, so I've clicked on that. Now the next one that I'm going to choose is titanium beta 215 and I add to the component. Okay, so we have added both our materials. Now if you see what in copper, like the first thing that is important is this geometric entity selection. So what this means is that at what all parts of your object will this copper be like present. So here you can see my entire domain is selected. Like you can see all the color, the entire object is colored in blue. It means for now, my entire object is made of copper, but that's not true. Like I just specified that my bolts are made from titanium. So now we are going to select on titanium. So you see in titanium, we don't have any geometry. So that is where this definition helps. So what you do is you go to the selection, you click bolts, and you see automatically all your bolts have been selected. And now COMSOL understand that this is made of titanium alloy. Okay. So this is the advantage of bolts. If suppose you didn't have this, you could have simply just selected on it, and in the same way as I selected before, and all your bolts will have been incorporated. But this is just to make it easier. Like if suppose in future also I need bolts, so I can just simply make the selection. I don't have to repeat that again and again. Okay. Now you see this interesting thing in COMSOL. After you have selected this titanium and you have specified the bolts, now copper, which was earlier defined to it, it has been overridden. So now copper is no longer be defined on the bolts, only the bus bar, the main body is made of copper. So this is an advantage in COMSOL, that you don't have to specify individually for each of them. It automatically overrides if suppose you mention some other condition on those boundaries. Okay. So any questions up till now? Okay. So you can see now in the order. Now we are going just in the order. After materials, the next one is to specify the physics. Okay. So you see in the physics, there are some default nodes like current conservation, electric insulation, initial values. So these nodes are default and we just can't delete them. Like they are there by default. But there are certain boundary conditions or certain constraints that we have to provide to COMSOL externally. And that varies according to our problem. Okay. So that is what you have to, that is what is the next step, is to add the physics boundaries and constraints. Okay. So now in this bus bar, we have to generate an electric current. So can anyone tell, like, to generate an electric current in this bus bar, what do we need? Like, how can I generate electric current? I don't have any wires.
Voltage at some of the bolts and a low voltage at the other bolt.
Yeah, exactly. So we will specify a potential difference. So at this bolt, I'm gonna specify a higher potential, and at this, I'm gonna ground. So this potential will be 0. So that will actually make my current flow in this bus bar. So now you have deduced that this is a boundary that we have to provide. So to apply any boundary condition, just right click on that particular physics. So here it is electric currents, right click on it. Now there's a boundary, these are various boundary conditions that are present in this physics. We are interested in electric potential. So I click on that. Okay. Now the first step again is to select the boundary. So this means that where do you want to exactly specify this electric potential? So I want to specify it here. So I have selected this. Now the next thing is, what should be the value of this electric potential? Now here comes the use of those parameters. So in the parameters, I have a variable named VTOT, which is 20 millivolts. You can see how these units are specified. They're always specified in a square bracket. So I'm going to use this parameter here and make sure that it is case sensitive. So this is okay. So you can see now my applied voltage of 20 millivolts has been applied here. Okay. So now what is the next condition? We have to apply a ground voltage to these 2 volts. So again, I'm going to right click on this. I'm going to choose ground. And what are my boundary selections? These 2 surfaces of these 2 volts. So you can see the equation here. What is the equation? B is equal to 0, which is zero potential. So that is what we want. Okay. So we have specified our potential difference that we wanted in the electric currents. So I guess we are done with this. Now the next thing is heat transfer in solids. Okay. So I'm gonna drop down. So you see there's some default nodes. There's a solid one. Now in the solid one, you see there are various material properties: thermal conductivity, density, heat capacity. Now, as I've added a material, COMSOL is automatically, I have understood that this solid is from that copper thing. Okay. So it has automatically reduced that, and it is automatically taking those values from the material. Now, if you see in the copper, if you go here, you see there are certain material constants: electric conductivity, heat capacity, and these check marks denote which all properties, material properties, are essential for our model. Like according to what all physics I have chosen, it has automatically checkbox those particular material properties. And this is what is being used in each of these physics. So this is done automatically. And the same is for titanium. Okay. So you don't have to like change anything. But if suppose you want to add user defined value, you click on user defined and you can define your own value. Okay. So I've made it all from material. These are certain initial values which you can provide, but these are like optional. If you don't provide these, don't affect until and unless it is a time dependent study. Okay. Then this is thermal insulation. Now, okay, so now what I'm going to do is there is this bus bar has air all around it. So there will be a convection which will be happening between the surfaces and the air. So I'm going to define that in my heat transfer in solids. So that is my boundary condition for this physics. So for that, you right click on it, you click on heat flux. Okay, so now you see convective heat flux. I'm going to click on that. And now you can specify the heat transfer coefficient. So suppose I chose it to be 5. Okay. But you can see like there's a parameter which is already defined in the parameters list, which is named as HTC. So I can use that parameter here once again, HTC. Okay. And this external temperature, this is the default one, 293.15 Kelvin. And now, so can anyone like tell me like where all do we have to apply these heat flux, this heat flux boundary condition?
To the bus bar.
Yeah, so basically we have to apply it on the entire domain except those 3 points where we had defined our voltage. Okay, so to do that, in the domain selection, first I'm going to click all my boundaries. Okay, and then I'm going to remove these 3 on which I had mentioned my voltage. So for that, you can see in the electric potential that boundary name was 43 and the ground was 8 and 15. So I'm going to delete them. So you go to 8 and you click this minus button. So it will be removed. Then the next was 15. So you go to 15 and you remove that. And the last one is 43 and you remove that. So you can see your entire domain is of blue color except those 3 points. Okay, so this is what we wanted. So now my heat flux boundary condition is fully specified. I have mentioned the boundary selection and I've given the appropriate values. So now the next step is multiphysics. So in this, you don't actually have to do anything. All the things are already specified. Like these are the 2 coupled interfaces that I have just mentioned, electric current and heat transfer in solids. And so if I click on equation, so you can see how it has transfer the information of one equation to another. So this equation it is getting from the electric currents, and this equation it is getting from heat transfer in solids. And this value it has derived from that electric current. So this is how is COMSOL actually bridging that gap between these two interfaces. Okay, so this is already specified. Now the next important thing is this mesh. So this mesh is like important because it actually divides your entire domain into various small elements. Okay, and those small elements, COMSOL will apply its physics. It will solve individually for all those small elements. It will integrate all of them, and it will give you the final solution. So okay, so if I just ask like which kind of mesh will be like better, extremely fine or extremely coarse? Anyone? Sorry.
Extremely fine.
Yeah, exactly. So we will use for extremely fine mesh, you will see that your entire domain will have very, very small but huge number of elements. So that means your all your calculations will be much more accurate. And but there is a problem, like it will take much more time. So there's always a trade-off between the computation time and the accuracy. So if you have chosen extremely fine, then it will have to do the calculations on each and every element, and that will take time. But if it is extremely coarse, then you don't have enough elements that it will give a accurate answer. So this mesh is always, it is like, this is the main thing in COMSOL which you have to decide upon to get accurate results. Okay. And there's another thing which is sequence type. So there are two ways, like first is a physics control mesh and the next is a user control mesh. So physics control mesh means that COMSOL, it automatically generates a mesh which is suitable for your physics and for your object. And in user defined, you can define your own mesh. If I go in mesh, you see that there are various operations like size, and there are various shapes also of the mesh, like it can be tetrahedral, it could be quadrilateral. So all these options are available. So that goes if you want to choose user control mesh, then you have to adjust all the mesh settings by yourself. In physics control, COMSOL does it for you. So now I'm going to keep it as physics control, and I will choose element size as normal so that it won't take much time also, and accuracy will be pretty good. So now you have defined both of them. Now you build all. So you see. So COMSOL has built a mesh for me, and it has automatically resolved. Like you see in this area, which is closer to the bolt, it has automatically made it finer because it knows that at this point, my accuracy or my results will affect the entire calculation. So it has automatically resolved it. And similarly here also. So this is physics control. Like it is quite smart in that sense, where to mesh more and where to mesh less. Like these points don't matter much. So it has made them coarse, and this, it has made it fine. So all this is done automatically. Now, after we have done this mesh process, the next step is to go to the study. So this is the study, and in the study, these are the study settings. So if these are generate default plots and the convergence plots. So what this means is that, like I told, that the entire domain is, it is being divided into small elements. So convergence is quite necessary, that if your solutions, because all these are numerically solved. So if all your numerical solutions are getting converged or not. So those all plots are generated, like how much error is there at each iteration. And these are some of the default plots which are being generated. Okay. So now I'm going to, this is step 1, stationary, and you can see all the physics interface, the multi-physics all have been selected. And these are some of the other settings which you can do. Errors and dependent variables. Okay, so we click on compute. So here this bar shows like how much study has been completed up till now. Yeah. So first of all, you see these convergence plots. So this shows you like how much error has been like there in the first 5 iterations, then in the next 5, in the next one. So you see so for convergence, there is a certain criteria, like the error has to go, it has to go below 10 to the power minus 5 or 6. That depends on the physics and the geometry, or you can specify it manually also. So that is the criteria that it has to reach, and some are their default settings. Okay, so that in this part you can see the errors, and this is like it is solving the electric currents and the time and the temperature. So I told you these are the dependent variables. So those are being solved, and this shows the error, which is there after each iteration. And once it has reached that criteria, it stops there automatically. Okay. So now we are the next step is to post-process the results. Okay, so first I'm going to show you temperature. So you see, this bar is showing you the scale, like the magnitude. So if suppose a thing is, if a certain surface is of this color, it means it has the very high temperature. And if it is very red, then it has a low temperature. So this is that scale, okay? And you can see that we had provided a potential at this point. So it is natural that the current will be, that the temperature will be maximum there. And we had ground both of these boards. So the temperature is quite minimum here. Now, there's one more interesting thing. You can see this bus bar. So you might recall that we had made this bus bar from copper, and these bolts were made from titanium. So the temperature of the bus bar, which is this dark, is less than the temperature of both these bolts. So can anyone tell like why it is happening?
The thermal conductivity of copper is high, so it is transferring more heat than accumulating.
Yeah. Yes, that's the right answer. So basically, this has higher thermal conductivity, so the heat transfer will be more, and that is why the temperature is less. So this is the result that we have got. Now we can play with it. So you can see I clicked on the surface. So currently I'm plotting the expression, which is temperature. Now I can vary this. Like suppose I make it cos t. This is just a random function, like it doesn't have any physical meaning. So you see, it has plotted in that sense. So basically this expression, you can like make it anything according to your convenience. You can define them according like what all expressions, any complex expression it can take. And there are some expressions which are already there in COMSOL. So to access that, what you do in the expression bar, there is this replace expression menu. You click on this, and now you go in electric currents. So you get various variables like normal current density norm. These are all the variables that you can plot. Like I just plotted temperature. Then this is current density, and this is an X component, Y component. So suppose if I go, and this is in heat transfer in solids. So I can choose a flux. So suppose I choose this one. So you see I chose that, and my expression has been changed to this. So if I plot this, so I'll get my convective heat flux. Okay. So in this way, you can choose any expression that you want from this menu, and in any of the physics, any of the expression that you want. Okay, so this is a kind of post-processing that is available in COMSOL, that you can generate these 3D plots and you can see all that magnitude. Then if we talk about electric potential, so in electric potential, this is called a slice plot. So basically it has sliced the entire domain in this way, and it is showing the electric potential along that sliced domain. So basically you can see that the potential is the maximum here because we had provided 20 millivolts here, and here it is here it is 0. So this is what is actually happening. Now, if suppose I want to change some settings of these planes, so suppose I can make it coordinates instead of 1. So if I specify this, so these are the coordinates of my X plane that I want. So this is the new plane that I have formed, and you can see this is 0 and this is 20 millivolts that we have expected, and this is the potential in between. So this is a glimpse of like what all post processing that we can do in COMSOL. In the further example, like I'll show you how to create plots as well. So if you have any doubts up till now, you can ask.
Can we add more of such planes?
Yeah, we can.
Like
Suppose if I change it to 5. So
Okay,
more
right.
planes are added.
Yes.
And similarly, you can do that in Z plane, and in X plane also you can specify the coordinates. And if you just right click on this, you can see you have various other options also. You can plot a surface, slice, iso surface, and arrow volume. So I'll explain all of this in further example also. Like we will create line graphs, like line plots and other things also. So in this, we have kind of explored this multi-slice and surface.
Ma'am, does it show animation at the final result?
Yeah, so there will be an animation also, but that animation could be created if we have a time dependent study that we will also do. So basically, like you simulate this entire model for about 15 seconds, and you are recording all the results at every 1 second. So it will create an animation of that, the results of all the 1 second, and create an animation. We will create that. So wait for that. Okay, so if no more questions, then we can head to the next example. Okay, so now we have covered this Joule heating. So I hope like now you are quite familiar like with how that workflow is going on, and it is very much in that order in which the COMSOL has provided, and how you add the parameters, what all physics is needed. So you're kind of familiar with that now. Now the next problem that we are going to deal with. So this is quite a very general problem that is done in fluid mechanics, which is laminar pipe flow. Okay. So basically, I'm going to take a pipe and I'm going to add a laminar flow in it, and we will plot like the velocity profile that is being developed in that pipe. And just for those who are like not familiar with this, so this is the equation of the velocity in the Z direction. So you see this is your Z direction, and this is the velocity expression in the Z direction for a laminar flow in a pipe. And you see that there are two constants of integration. So that means that we have to specify two boundary conditions. You remember that the fifth step is to add the boundary conditions and constraints. So that is actually being specified by these ODs, by these PDs, which we are not like at this point we are not aware of that, but now you can see that this is the equation for velocity, and you need two constant. There are two constants, so you need two boundary conditions. So first boundary condition will be provided at r is equal to 0, and the next boundary condition will be provided at r is equal to r. That is how we will solve this velocity profile, and that is what we will define in COMSOL also, and you will get the results. Okay, so this is the problem. Now I'm going to do that. Okay, so now I'm going to start a new model. So again, we are going to go to model wizard. And now we have a 3D problem. We have a pipe. So I'm going to choose that. Yeah. So now in our problem, it's basically we are passing a laminar flow of fluid through the pipe. So in this case, now we don't have two physics. We just have a single physics, which you will find in fluid flow. So in fluid flow, you have all the physics which are related to fluid mechanics. And here you can see there are various sub-physics: single phase flow, multi-phase, porous, particle tracing, fluid structure interactions. So basically, like if suppose you have a solid and you're passing fluid over it, so that becomes a fluid structure interaction problem. And thin film flow, rare fields. So our problem is based on single phase flow, and we are going to click laminar flow. So you can see laminar flow. So I've selected on it. Now you click on add. Now I've added the physics, and these are all the dependent variables. So basically in laminar flow, we are usually solving for velocity field, and which has three components: U, V, W, and a pressure. So now we go to study. So our study is again stationary, and I've added that study, and now we click on done. Okay, so now we have this. So the first step is we have set up the model environment. Now we are going to make the geometry. So now I'm going to make that geometry from scratch. So to make any kind of geometrical object, if you right click on geometry 1, you will see all the possible 3D. Since we have chosen the dimension as 3D, so it will show all the possible geometrical objects in 3D. Okay, so I want to choose a cylinder for a pipe. Okay, so now the dimensions of our pipe are as follows. Our radius is, so you see, even though this is meters, but I can specify this in other units also by using a square brackets. So my radius is 1 centimeters. So you see, if you write this, then COMSOL will automatically understand that this is 0.01 meters. Okay. Then my height is 10 centimeters. So, and it is of solid type. And now you can position it. So this, I position it here only. And my axis type is Z axis. And this is my work plane. So now you build selected. So you see, now this is a kind of cylinder, your pipe, which is being generated. And these are all the coordinate system it is showing. You can select on it and you can click on this button, zoom to extend. So it will keep you in that zoom. Then after you have built the geometry, so the next step is to, like, we don't have any material kind of thing here, so it will like take that for default. Like there are some default settings for material, so it will take that, but we don't need them here. Okay, so we skip that and we go to the physics, which is laminar flow. Now in the laminar flow, you can see the equation that are being solved. So this is the equation. So I guess the third year students will like understand all of this. Maybe second years won't. So no issues. I just have gave you a glimpse, like we need to specify two boundary conditions, inlet and outlet. So we are going to do that. But these are some additional settings, like you can specify what kind of flow you want. So if this is an incompressible flow, so here density is constant. And turbulence, there's no turbulence. We are simulating a laminar flow. This is some temperature and pressure. Okay, so now these are some default nodes and we are going to go through all of them. So first is fluid properties. Now in the fluid properties, I'm going to mention my properties user defined because I have not mentioned any material. So if suppose in materials you would have chosen water, so it will have taken the density and the dynamic viscosity of that material. But here I'm user defining it. Okay, so this is 1000 kg per meter cube, and this is what I want. So you see how I have chosen it. I've clicked on this drop down menu. I've chosen user defined. Now my fluid is Newtonian. Then you go to dynamic viscosity, which I am going to define user defined. And this I am going to keep as 10 to the power minus 2 pascals into second. Okay, so I have defined my fluid properties. Now I'm going to, these are my initial values. So these won't matter much if you are like doing stationary study. So you can keep them as default only. And so you see, now if I click on wall, so in wall, what basically is being happened, there's a no slip boundary condition which is being applied. You can also apply some other slip conditions also, like electroosmotic, leaking wall. Here we have a no slip condition on these walls. Now it is being applied to all the domains, but we don't want them because we don't want this upper circle and this lower. We don't want these to be no slip condition. We just want this curved surface of the cylinder to be a wall. So for that, if you add more boundary conditions which will specify these circles, then it will automatically be overridden, as I had shown earlier also. Sorry, someone was saying something. Okay. So now, first of all, we are going to specify, and so basically you just think like if you have a cylinder, now you have to mention like from where exactly is your fluid going to come and from where exactly it is going to come out. So that is what we are exactly going to specify in the boundaries also. So for the boundary condition, you right click on the laminar flow, you choose inlet. Okay. So the first thing that we specify is where is my boundary. So if I suppose there are two circles, you can choose any one. I choose it here. Okay. Now I have chosen my boundary. Now I am going to specify inflow velocity, which is exactly like at what velocity is my fluid coming through this inlet. So I'm going to specify that as 0.05. Okay, so I have chosen that. This is there are also other boundary conditions like pressure, mass flow, fully developed flow. I'm just going with this normal velocity. Now the next boundary condition that we are going to specify is outlet. Now in the outlet, we are going to first specify what is my boundary. So the first one was the inlet, so the second one is the outlet, and it is going to be like a static pressure, like the P0 is 0. So remember this P0 is with respect to a relative pressure, and that is why we have mentioned here as 0. Otherwise, it would have been atmospheric pressure. Okay. So we have done that. Now we are completed with our this physics. Now we go to mesh. So again, I'm using a physics control mesh, which is maybe we can try find one this time, and we build all.
Hello, like I have one doubt. Like
Hmm.
if the fluid is flowing through a annular section, then how will we show it?
Like you mean that radial circle in that direction, in
I
that.
mean that there is two pipes. One is inner solid pipe and the outer pipe, and through the vacuum between the two pipes, fluid is flowing. Then, like, could I explain myself? Like a cylinder, and covering the cylinder there is a pipe, and through the external pipe the fluid is flowing.
Okay. Yeah, I got it. So for that, like this geometry, like there are various operations in geometry, like I also just mentioned, like in the busbar also, you could see like there was so many operations involved. So more and more complex geometry that you want to make, then you have to explore all these different options which are there in geometry. But yeah, it's possible that you can make all those things as well. Otherwise, like in the post processing, I will show you like there's a way that people simplify these 3D problems. So maybe that might answer your question. Okay.
Thank you.
So our meshing is done. So now we click on study and we click on compute. Maybe it's the fine mesh that is taking time.
Meanwhile, could you re-explain what you meant by when you're talking about the static pressure? You set it to 0 pascals.
Okay, so basically there's a reference pressure which is there in this laminar flow. If you click on it, that is automatically set to the atmospheric pressure. So when I'm calculating that P naught, it is relative to that P reference. So that is why I mentioned that as 0, so that it is automatically set it at P reference, which is the atmospheric pressure.
And that is for the inlet and outlet both? Is that the
No,
case?
it's just for the outlet. In the inlet, I mentioned the velocity. So from that, pressure will be calculated.
Right. Okay.
So,
Ma'am, one more question.
yeah.
Can I ask?
Yeah.
Actually, did you put the mesh size same for all together for the cylinder? Because
Sorry?
near the boundary, you put the mesh size same for all the body of the cylinder. Because for the cylinder, near the wall there will be no slip condition. So
Yeah.
should it be same the mesh size, or it will be different for different section?
So that is what is the good thing about COMSOL is when I have chosen as physics control, so it will automatically like resolve the mesh at those places where it is needed. So you don't have to worry about them. So as you just mentioned, like at these corners of the walls or something, there it will be resolved. Like I can show you the mesh once again after this is done. So you can see all these convergence plots which are coming. So these are all the errors. So with each iteration, the error is decreasing.
Like in the previous problem where we are where it's shown the convergence plot. In that case, for two different dependent variables like temperature and electric current, the tolerance level was different.
Yeah.
So this is already been determined in the COMSOL, or can we change this tolerance level?
Yeah, so there are some default values and you can also manually change it. Like if suppose you want your results very much accurate for research purposes or something, you can't define it. So I'll show you in a second, like just after this is completed. Okay, so this is done. Now, so as you just asked about those tolerances, so there's something called solver configurations. So in that, you can see if you go to stationary solver, so this is my advanced. So you can see like there are various settings that you can do. This is fully method and termination. So this is a method that you are using, like it can be automatic Newton, it can be constant Newton. These you will study in your numerical methods course. And there are also certain other like tolerance factor that you just asked. So here it is 1. and the maximum of iterations are 100. So if you want more like accurate results, you can increase or decrease it accordingly, or you can run it for more iterations. So all those settings are internally in the solver configurations, and you can do them. So if I just do these settings, I will again run the study and it will be computed along according to that. Okay. So yeah. So you can see like we have the results. So this is velocity, and now we're going to post process this. So now it is simply like slice. It is showing you slices. But what we can do is there's a thing called data sets. So this is very important. So now suppose instead of this, I just want to see my velocity profile in a circular surface, which is at a depth of 0.05 meters. So I just want to see my velocity on that surface. So that is an example of an iso surface. So what I will do, first I need to choose a plane surface, and then it will plot on it, on that. So for making that, you click on data set. So in data set, what actually happens is all the important data that will be needed to plot your graphs or anything in these results section, you make it here. So if suppose I want to create a new data set, I right click on this. Now there are various options. First is you can cut a plane, and this is what I want. And then other options are like you can choose a line in this, you can choose a line in 3D, and then you can plot along that line. Okay. And then you can choose a point in 3D and you can plot on that point. So these are various data sets that you can generate within your domain, and then you can plot on that data sets. So here we are choosing cut plane. So now my plane will be in the XY plane. And my Z coordinate, I'm going to choose it somewhere between, so that because to avoid any boundary effects that might happen. So I'm choosing it in between. So I've chosen 0.05 meters. I'm going to click on plot. You can see I have created a surface at the middle of this cylinder, and I'm going to plot my velocity profile using all the data on this surface. So this is what is meant by data sets. And you can create other data sets also. I'll create more. Now, first we are going to plot on this. So for that, now you see like to plot more graphs, you click on results and you right click on this. So you see there are various plot groups, 3D, 2D, 1D. So 1D plot groups are like line graphs. 2D plot groups are like showing the contours on a surface. 3D plot groups are like, which I just shown you, like the entire domain, and it will show you at different points in the entire volume. Okay. So here we are interested in 2D. So I click on that 2D plot group. So I've chosen 2D plot group. Now in the 2D plot group, you again right click on this, and there are various subplots within this 2D plot group. You can plot a surface, you can plot an arrow surface, you can plot contours, streamlines. Streamlines are used for if suppose particle tracing or fluid lines and all these things. So we are doing surface. So I've chosen surface. Now if we go to the 2D plot group, now there's a section called data set. So here it is being used. So we will use a data set of this cut plane one. So I'm going to choose that. Okay. And all the settings are just the same. Then I'm going to the surface. So you see, this is my expression, which is velocity magnitude. You see, this is the description, velocity magnitude. So on this surface, the entire velocity magnitude, this expression is being plotted. Okay. And it is very much like in, it is very much in agreement with what we had expected. Like since we had a no slip boundary condition on these walls, so you will expect your velocity to be 0 at these boundaries. Okay. And at the center, the velocity will be maximum. Okay. And this is what we are getting, like this is completely red. So this is a very good way, like these are various ways you can see your results, and you can report your results through these 2D plots, through 1D plots. I'm going to show you how to make a 1D plot also. So this is how you create a 2D plots. Okay. You have to always remember, you have to always choose a data set which will be obviously a plane, and then you choose a 2D plot group, and then you choose surface, and you can plot any expression you want. So here it is U. Okay, so now we are going to also plot a line graph of the velocity. So for that, again, I'm first going to make a data set. Now, can anyone tell, like, for a line graph, which data set will I choose out of all these? Any guesses? Anyone? Sorry, I'm not able to hear you.
Can you repeat your question?
Yeah, so I mean, like, now I'm going to plot a 1D graph, like a line graph. So which data set will be like the most appropriate for that? Just like I needed to make this 2D plot, so I chose a cut plane because I needed a surface, so on which I will make a plot. So for a line graph, I need a line in 3D because my my entire domain was in 3D. So I will choose this cut line 3D. Okay, so what basically it will do is it will cut a certain line in my entire domain, and my entire graph will be plotted on the data points of those lines. So if you see your geometry again, so if suppose you see your velocity is varying along the radius. Okay, so if suppose I cut a line on this along this radius of the cylinder, then I will get, because you can see from the surface plot, your velocity, if you make a line here, it is varying along with the radius. So if you make a line along with this, you will get points on that line that will show you what is the velocity on each point, and that will give you the graph of velocity versus the radius. Okay, so for that you need a line. So I'm gonna make a line in 3D along that radius and at a depth of 0.05, just to avoid any boundary effects. So I'm choosing this as 0.05, and my x will be, since my radius was, so this is, the origin is at the center, so I'm going to make it from -1 centimeter to +1 centimeter. So it is -0.01 to 0.01. Okay, and my y coordinate is 0. Let's plot. So you see, this is a line. If you see from above, this is a line which is along the entire radius, and I'm going to plot my velocity on this line. Okay, so now you have chosen your data set. Now again, you go to results, you right click on this. Now we are going to make a 1D plot group. So in 1D plot group, you again right click on this and you choose a line graph. So basically now we are making a line graph. So we choose that. Okay, so now you have to mention from which data set do you want to take that. So you take that from cut line 3D. Okay, and now you go to line graph and see, this is your velocity profile. And this is the expression that I've added, velocity magnitude. Okay, so you see, like, along that line, how that velocity is varying, it has created a plot of that. So this is basically what all you do in post processing. So if you want to make a 1D plot group, you have to make a 1D, you have to choose a one-dimensional data set. If you want to make a 2D plot group, you have to choose a two-dimensional data set. Okay, so that is the main thing that you have to remember to get any kind of results. And then you can just manipulate all these expressions that I've just told. Like, you can replace it with any of the variables. Like, suppose we choose it velocity field. We know that velocity is in the z direction, so we plot that. So it is coming in the opposite direction because my inlet was up and my outlet was down. So it's the coordinate. So this is how your velocity is looking like in the z direction. So in this way, you can plot all the variables. Okay. So this is what all the plots and surfaces and the data sets. This is how you can do all that in the results section. Okay. So any doubts up to now?
Hello, ma'am.
Yeah.
Can you repeat 1D plot again, please?
Okay. So in 1D plot, so basically for a 1D plot, you will need a 1D data set. By 1D, here the dimensions are a bit confusing, but just remember, like 1D data set, 1D means a line here. So for a 1D plot group, you need a 1D data set. So for that, you can do what? You can make a line in your 3D. So that is why we created a line in 3-dimensional, which was this line. Like I mentioned, this coordinates, and this is along the radius of the pipe. Okay, so this is the line that I have drawn. And how I come to know that my velocity is varying in this direction? From this plot, you can see that if you take a line along this radius, at each point my velocity is varying. There is no point in taking along the y or the z direction, because in that the entire velocity is the same, so you won't get anything. The velocity is varying along the radial direction. Okay, so that is what you'll get. And now I chose a 1D data set which was along that radius by specifying my points. Okay, and after I have done that, now I choose 1D plot group 4 by right clicking on this 1D plot group. Okay, now I've added 1D plot group. Now you again right click on this and you get line graphs. So this is what we want. So I chose that. I got a line graph. Now in the line graph, first of all, you have to specify this data set. So the parent of line graph is this 1D plot group 4. So what I do is I specify the data set in this cut line 3D1. So now it will take all the data from this line. Okay, now you go in line graph and it is taking its data set from the parent, which is cut line 3D1. Now you can plot any expression that you want. You can specify this, and this is the y-axis. You can specify the x-axis. Like if you want to specify some other expression, click on expression. Then you can specify the expression. Now, like my radius is along the x coordinate. So I click on, I type x coordinate, and it is plotted. So you see this is my x coordinate. So this is how you have created a line graph out of this 3D object. So is it clear now?
Yes, ma'am. Thank you.
Yeah. So what people generally do is the question that was being asked by someone like that annular pipes. So we know that my velocity is like varying along the radius. So people, what they do is they initially simulate all these things on a simple 1D line, which I have just taken. You see in this cut line 3D. So I have taken a 3D geometry. People, to avoid any kind of complexity, they just simulate on this line, and they apply the boundary condition on the end of these two, on the end points of this line. Like on this condition, there is no slip, so my velocity will be 0. And at the center of this line, my derivative of velocity is 0 because it is maximum here. So by applying these two boundary conditions, you can specify your entire velocity profile that you want in a pipe. But in that, you won't get any 3D visuals. You will just be able to plot a line graph, which I just plotted. So if you, as you just asked that question, so for that annular pipes, maybe people can choose some 1D or 2D things, and they can plot it much more easily than doing a 3D geometry, because it is much more complex to make. Okay, so that is what people usually do. Like if suppose you have a slab and you want to see how the temperature is varying. So you know the temperature is varying only in x direction. So why make the entire cuboid? You just take a line and you vary the temperature by finding the boundary conditions. So that is how people usually simplify their problems. and avoid making 3D. But in 3D, you get all these visuals like these how it is exactly varying. These 2D plots you get, these are not which you will get in 1D. So that is the advantage there. Okay, so
Even
that
in
is
1D, like you were talking in this example, so
yeah.
simulating on a line, if we want the case for annular regions. So like how would we add input and output velocity? There would be no inlets and outlets, right?
Yeah, like I was just giving an example, and maybe 2D will be more sufficient there. So
Okay. Right.
just a way to, like, people usually simplify their problems by going one dimension down. If they know
Okay.
like their
Symmetry.
variables are varying in, yeah, their variables are varying only in one direction. Maybe in annular, you can use an axisymmetric. You can just plot half. You can vary your dimension, vary your variables in only half of the section, and that will automatically get updated for the other also by using axisymmetric dimensions.
Right,
So,
right.
so all those simplifications are obviously like there. Just if it is easier to make, then you can choose 3D, and then you can get all these like visuals of how all these contour plots and all. So that is the thing. Okay, so any doubts in this example? Okay, so maybe so since we have not much time left, we can go to the last example then, which is that animation thing that one person asked, and it is based on time dependence. So the last two problems were stationary. So now we are going to do a time dependent study, and the problem is simple. Like, you have this geometry, you have a this is 2-dimensional, so you have a square and there's a hole which is circular, and then you are going to provide various boundary conditions of heat all around these boundaries and in the circle. And then you will see like how with temperature, how with time the temperature is varying in this solid, which is in 2D. Okay, and then you can create an animation also of that, and you can see how with time, as time progresses, how temperature varies. Okay, so this is the next example. Now I'm going to simulate that. So again, we are going to choose a new model. Now we click on model wizard. So now you see our problem is 2D. So we click on 2D. Okay, so this is simple heat transfer problem. So we go to heat transfer, and since this is a solid, so we choose heat transfer in solids physics. Now you add this. Okay, now the temperature, the dependent variable is temperature. Now you go to study. Now we are going to choose time dependent study. You have added the study. Now it is done. Okay, so now we have this, and so we have set up a model environment. So the next step is to define the geometry. So as I've shown you, this is our geometry. So for that, I will need a square and a circle. So for any kind of geometrical objects, right click on geometry 1. So first we are going to make a rectangle, and it's a square, so you can choose either of them. It's of 10 centimeter by 10 centimeter, and I'm positioning it such that its center lies on 0,0. You build selected. So this is made. Now we need a circle also. So we again right click on the geometry 1, we choose circle. Now the radius is 2 centimeters. Sector angle is 360. We need the whole circle. And now it is again centered at 0,0. I build selected. So I have this circle in the center. Now we need to create a hole. Like, there's air, you can imagine there's air inside it. So we need to create a hole. So for that, what you do in geometry, by right clicking, there's an option called booleans and partitions. So you click on that, and there's an option of difference. So difference is just like subtracting. So I click on this. Now difference is basically you select two surfaces, two 2D objects, and then you take a difference of it. So basically this one will be, this one will get vanished. So objects to add is this entire, and objects to subtract is this circle. Okay, and this is the two options. Now you click on build selected. So you see this circle has been subtracted from this whole 2D thing. Okay, now we are done with the geometry. We have specified this. Now we will go to materials. So this 2D object is made of iron. So we right click on this and we add a material from the library. We click on built-in library, built-in materials, and then we choose iron. Here it is, and you add to component. Okay, so you close this. Now you want it is all automatically applied to all domains, or you can check also. This is all domains, and these are various properties of iron that are essential for this. You just need heat capacity, density, and thermal conductivity, and that is automatically done by COMSOL. Okay, so this is done. Now you have assigned your material. Now you choose now you come to the physics and you have to specify certain boundary conditions. So the boundary condition here is that inside there is convection happening, because you can imagine there's air inside, and then on these two surfaces there is a temperature. On this surface there is a flux, and on this it is thermally insulated. So this will be a condition. So first I will take you through all the default nodes. So first is that same solid, and again we will choose the material properties from material. It will automatically take in. Then there's an initial value. So here now it is time dependent, so that matters. So initial values is actually at time is equal to 0, what will be my initial temperature. So I make it 100 kelvins. Okay. Now thermal insulation. So you see now thermal insulation is present on all. But if I add on more boundary condition, this will be overridden. Okay. So now we will have to add more boundaries. So first condition that we will add is temperature. So this will help you specify a temperature at any boundary. Now on this left and the right boundary, I want to specify a temperature, which is again of 100 Kelvin. So I did that. So first I selected the boundary, which is this and this. It is shown. Now you specify the temperature. So this is done. Now we are going to specify zero flux at this bottom side. So you right click on heat transfer in solids, you choose heat flux. And now you select this boundary and you make, so there are three options of flux: convective, general, and heat rate. So I'm going with general and it is 0. So this is 0. Now you see that if you go to thermal insulation, this one is now thermally insulated and this one, because these are the two boundaries that are still undefined. But this we want to be thermally insulated, so we won't touch that. Now we will specify a heat flux in this region. So for that, you again right click, you choose heat flux, and now this entire circle you are going to provide convection to it. So you select all the boundaries, and now you are going to click on convective heat flux to provide this boundary condition. Now my heat transfer coefficient is 5, and my T external is going to be, let's say, 5 Kelvin. Okay, so now we have fully specified all our boundaries, and now we can go to the, so you see here there's no multiphysics because there's only one physics. So multiphysics is when we have 2 or more physics involved in the simulation. Now you go to mesh, and again I choose physics control mesh, and I do normal to build all. Okay, so now we have done this. Maybe we can make it more fine. So you see, like all the surfaces which are near to this circle, they're automatically resolved and made finer. And these outer surfaces, these surfaces are made a bit coarser. So this is automatically done by COMSOL, like which all parts of the domain are more important to our calculation and which are not. Yeah, where there is a possibility that the results might get deviated or might not converge. So it automatically resolves the mesh in those regions. Okay, so now you have done the mesh. Now you go to study. So you go to time dependent study. So you see in time dependent study, there's an output time. So this means like range means in which range you want to run your simulation. And this middle number means like at which time do you want to save your results. So here it means that I want my simulation to run for 1 second, 0 to 1, and I'm going to show my output at an interval of 0.1. This is the notation. So now I'm making 1 second to 50 seconds. Okay, so now all the things are specified. I click on compute. Okay, so first you see at 0. I've chosen the time as 0. So this is in my results. So in results, temperature, and you go to time, you plot 0 seconds. At 0 second, everything is 100 Kelvin as yet specified. Now, as you increase time, I go to 0.1. So you see the temperature is in this region, it is decreasing. There's convection going on. And here it is still 100. Then as you make it 6.8 seconds, so the effect is happening. Like here now the temperature it's like slowly and slowly the effect is being transmitted to other sides of the 2D object. Like the first one which is exposes this circular region to the convection, and slowly like these outer surfaces, their temperature will also decrease from 100. But in here now this is 100 and this is the temperature is decreasing in this region. Now if you increase more time, now you make it 27.4 suppose. So you see now the temperature is decreasing to a far extent, and at 50 seconds you plot. So this is the final picture at 50 seconds. You can simulate for much longer time, and finally all of this will be at the same temperature as the temperature which is here, 5 Kelvin. Or like it can vary, like we have specified some boundary conditions just randomly. But if you choose the boundary conditions which are quite physical, then you can actually get those results. Okay. Now, if you want to create an animation, so what you do is in this temperature, there's an option here. You see animation. You click on this, you choose player. So what it will do is it will create an animation of every second. So you see this animation is created. This is a play button. So from 0 second to 50 seconds, it is showing all the scenarios at every 0.1 second interval. So in this way, you have created an animation for the temperature. Similarly, you can do this for other variables also. You can plot other variables and you can create an animation of them. So, and you can then easily export them also in MP4 or something, and then you can share it with other people also. So this is temperature and this is surface plot. You can similarly, you can also plot other things as I have told earlier, also isosurface, slices or something like that. Like here you can see the option is of surfaces, contour plots. So you can plot all of them, which is relevant to your problem. Okay, so yeah. Any questions up till now? So this is basically like what happens in time dependent study. You basically simulate at for some time and you report results at certain intervals, and then you can plot those results and you can get all the you can plot graphs also which are there at different times. Maybe suppose let's plot a graph So for a plot, like you see in this, I have to cut a line in 2D because I have a 2D object. So I cut a line in 2D. Suppose I cut it along this, that how the temperature is varying along this direction. So my coordinates x will be from minus 0.05 and y is 0.02 and this is 0.05. Maybe you can make it a bit upper. Okay, so this is the line, and along this line, I will plot my temperature at different times. So I've created the data set. Now I click on results. I choose a 1D plot group. So just remember that unlike in the previous example, it was 3D. So I cutted a line in 3D. So cut line 3D1. Here it is 2D. So you need to choose cut line 2D1. Now here in the data set, you choose cut line 2D1. Time selection is all. So it will create a plot for all the times. And now you right click on this, you choose line graph. And now I want to plot temperature. I plot. So you see, so these are all the times, like at every 0.1 interval, it is showing the temperature of all those at all those times for that line, on that line. Okay, so you can see, you can minimize the number of time at which you want to plot from here. Like you can choose it manually also, at which time indices you want that. So all those stuff you can do, but this is a kind of like, this will give you an experience like how you actually post process your results in COMSOL. Yeah, so any questions?
In the initial value that we specified, so you had said
Yeah.
that we only need to specify that in time dependent cases. So in the stationary steady state cases, does it use it as an initial guess or what?
Yeah. So you can consider it as an initial guess for numerical methods that we did. So if suppose your equations are like your problem is like it is converging automatically, doesn't matter much. So then initial value would matter. But if suppose in some hard problems where actually initial guesses matter, so in that initial values matter. So basically people don't like, we usually keep it as default, but sometimes if you're not able to converge your solutions, then these initial values, like they quite help.
All right, thank you.
Any other questions from anyone, like any doubts or something? Okay, then, so I'll stop sharing. So yeah, that was all. Like we covered 3 examples. So we covered 2 stationary problems, 1 time dependent, and we covered 4 physics like heat transfer, fluid, and electrical, then 1 physics also. And then we also learned like how to post process your results by plotting various graphs, 1D, 2D, and 3D plots. So I guess like this is basically what is the workflow and what you usually require in any kind of simulation. And yeah, so that's all from my side. Thank you.
So please fill the form if you want to receive the recording for the session. It is given in the chat. If you have already filled the form, then you can leave maybe. Recording stop कर दिया.